Okay, so the steps for doing a confidence interval for means is going to have some very similarities to proportions. We want to state our assumptions, we want to set up our formula and actually calculate the interval, and then we want to write our conclusion based on the context of the problem. And just like proportions, there is a set sentence that we're going to memorize and associate with confidence interval of means. We are blank percent confident that the true mean in context, so whatever the mean happens to represent, puppies and bubblegum, whatever, is between this value and this value. Okay, so assumptions for a t-inference procedure. We assume we're dealing with some sort of SRS, or there's some sort of randomness built in, and that can be either stated in the problem or it can be assumed as reasonable from, I guess, common sense. Since we're dealing with a t-interval, then one of our assumptions is that we don't know the population standard deviation. And then the third one is that we are dealing with a normal or approximately normal distribution of some type. Now, we can state this by saying we're told it, be in a given sentence in the problem. We could have a large enough sample size, meaning 30 would be enough. Or we could check the graph of the data to ensure that it is normal, and this could be done through histograms or box plots or normal probability plots. So any of those graphs that confirm normality would be fine to use on that. We only have to use one of those three methods. So if they tell us that the data is normal, we don't have to check it. And if we know that the sample size is large enough, we don't have to check the graph. So really we only check the graph if we're not given the first two cases. Okay. Now, the word robust is an awesome word, by the way. We refer an inference procedure being an inference procedure, so these confident level processes, to be robust if the confidence level or p-value doesn't change much if the normality assumption is violated. So in other words, if the data isn't normal and yet I'm still able to calculate a reasonable p-value, then we say that the data or the process that we're using is a robust process. So if we start over the normal curve but say some sort of skewness or some sort of strange violation of the data, the tails are really what we're looking at when we're talking about p-values here. So the area of the tails is actually going to be the same even if the center of the data is slightly skewed. And then just kind of a reminder, student t-distributions, the t-scores, are the statistics of smaller samples. So when we talk about it being significant, we talk about it being that the area under the tail of a t-distribution is larger than the area of a tail of a normal model. And so it's harder. In other words, the data has to be more significant in order for it to be considered rare or unusual, and when we're looking at it using a t-distribution. When we look at our data, we can handle skewness to a small degree, but if there's outliers, that will have a huge impact on our overall conclusions. And then if our sample size is really large, then we can handle more skewness in our data. But anyways. Okay, so we're going to go back to that problem we looked at the start of class. I'm sorry, of the start of the video series on using z-scores versus t-scores, and we've discovered that we can't use z-scores anymore. So I'm just going to show up all the assumptions and steps just to kind of get it associated, what the problem should look like. So we assumed that we had a randomly assigned treatment. We were told that the blood pressure was normally distributed. And so we're also told that, they didn't state the sigma, so we just mentioned that we didn't know the sigma. And then we just fill in our numbers from there. And then there's the conclusion on that. Let me pull up my calculator and show you how to type it in to get these numbers. And then, of course, let me show you a menu that we can refer to that will speed up the process as far as calculating the confidence interval. Okay, so if I want to do this by hand, I take the 2.056, so take the t star, times it by 9.3 divided by the square root of 27, and that's going to give me a number, 3.6. So I want my point estimate, 114.9. I'm going to add that 3.6 to it, and that'll give me 118. So that's that top number there, 118.8. And then I want to take the 114.9 and then, I'm sorry, let me try that again. 114.9. I want to subtract off the 3.6, and that gives me the bottom estimate of 111.22. Okay. The other way we could go about doing this, and this sort of speeds up not having to type it in step by step, is we can go to our stat menu and go over to tests, and we want a t interval. Okay, we want a t interval, so we're going to go to 8. At least on mine it's 8. And then it actually gives us two choices here. It says, do you want to input the data, or do you want me to look at the data individually, or do you want to type in the statistics of the sample, and then we'll calculate the confidence level from there. Well, we were given X bar, so we'll type that in. So that's 114.9. The sample standard deviation is 9.3. Notice I'm not worrying about n right now. Okay, now I'm worrying about n. We have a sample size of 27, and I want a confidence interval of 95%, so 0.95. And then the great thing is, so we hit enter, and the calculator will go ahead and do all this for us. So they will actually, the calculator, knowing the sample size, will adjust our standard deviation to match what the formula says. So if you do it by hand, we got to divide 9.3 by the square root of 27. Whereas here the calculator will work it out for us and will actually give us the right numbers for the confidence interval. Okay. All right, so another example. A medical researcher measured the pulse rate of a random sample of 20 adults and found the mean pulse rate of 72.69 beats per minute with the standard deviation of 3.86 beats per minute. Assume the pulse rate is normally distributed. Compute a 95% confidence interval for the true mean pulse rates of adults. Okay, we'll just kind of talk through the assumptions and make sure that those are valid, and then we'll jump to the calculator and make sure we can type this in. In the first sentence it says random sample, so we're good. We are told to assume it's normally distributed, so we don't have to worry about that. The standard deviation they give us is of the 20 samples, not the population, so I don't know the population standard deviation. So far we're good. We can go ahead and proceed with typing this information in. So we're going to pull out our calculator, and we're going to go calculate the t interval here. So we want to go to stat and then over to test, and we want t interval, and I'm going to type in the statistics that they give us. They give me all the interesting things. So they said the mean was 72.69. The standard deviation of the sample was 3.86, and there was a sample size of 20, and I want a 95% confidence level. So I'm going to hit enter and let the calculator do the math for me, and I get a confidence interval between 70.8 and 74.5-ish. So I can write that up as my conclusion on that. So we're 95% confident that the true mean pulse rate of adults is between 70.8 and 74.497. Okay, so sort of a side question is, another researcher comes on and claims that the true mean pulse rate is 72 beats per minute. In other words, I collect this sample and he goes, I think it's this. Well, does our sample support or refute this, and sort of explain why? Okay, well, let's go back. Let's take a look at what our confidence interval said. So our sample estimate was 72.69, but we got a confidence interval of 70.8 to 74. So the guy's suggesting then that it's got to be 72. Does our confidence interval support that? Well, 72 happens to be inside the confidence interval. So at this moment, we have no reason to doubt that that particular claim. So as far as we can tell, yeah, sure, it's got to be, 72 is fine, because our confidence interval suggests that it's got to be somewhere between 70 and 74. So anyways, another example.